Welcome to this Maths Made Easy video on stationary points. To start with, let's take a look at finding stationary points. So to find a point where the gradient is 0, we need to set dy by dx, so dy by dx, which is equal to f prime of x, so f prime of x equal to 0. So let's say we've got a nice easy function. Let's say we've got y equals x squared minus 1. Okay, and this is a sketch of this here. So this is y equals x squared minus 1. Well, we know that the gradient is given by dy by dx. So dy by dx, calculating dy by dx here, that would simply give us 2x. So setting dy by dx, which is equal to 2x, equal to 0, well, if we solve for x here, that just gives us x equals 0. So, for the value here then, y is equal to 0 squared minus 1. So therefore, y is equal to 0 squared minus 1. And in that case, that gives us minus 1. And we can conclude then that y equals x squared minus 1 has a stationary point at 0 minus 1. Okay, and we can see that from our graph here. Okay, 0 minus 1 here. Okay, so that gives us everything we need there for finding stationary points. Moving on now to find stationary points of complicated functions. So if we let y equal sine x plus cos x for x measured in radians, all we want to do here is find the stationary points in the range 0 to 2 pi. Well, if y is equal to sine x plus cos x, the first thing we need to do is find dy by dx. In this case, dy by dx, we'll differentiate term by term. If we differentiate sine x, that gives us cos x. And if we differentiate cos x, that gives us minus sine x. Okay. Now, to find the stationary points, we set dy by dx equal to 0. So cos x minus sine x is equal to 0. And in that case, we can set cos x equal to sine x. And if we divide the left-hand side and the right-hand side here by cos x, then we get tan x equals 1. Okay, just using our trig identities. In that case, we can simply find x by taking tan inverse of 1. So x is equal to tan inverse of 1. And that would give us two solutions here. That would give us pi over 4 and 5 pi over 4. Okay. So therefore, for x between 0 and 2 pi here, in the correct range that we have the stationary points. So remember, we've got two values for x here. So what you need to do is substitute these into this equation for y. So y is equal to sine of pi over 4 plus cos of pi over 4. And if you do that, you get root 2. So we have the stationary points. We just write this down in full. So we have the stationary points here of pi over 4 and root 2. We also have here 5 pi over 4, 5 pi over 4. And then if we substitute 5 pi over 4 into this equation here, sine of 5 pi over 4 plus cos 5 pi over 4, that gives us minus root 2 there. Okay, so that gives us our solution there to that example, and that gives us everything we need there for finding stationary points of complicated functions. Moving on now to finding the nature of stationary points. Once we find our stationary points, we need to find out whether they are a maximum, minimum, or a stationary point with inflection. And we do this by differentiating our derivative again. And we can see from this flowchart here what we should expect. So if we start with our function here, y equals f of x, well, we differentiate here to get dy by dx equals f prime of x, and we set that equal to 0. And we need to differentiate again for the second derivative. Now, if the second derivative is less than 0, that implies this is a maximum. If the second derivative is equal to 0, then that tells us that's a point of inflection. And if the second derivative is greater than 0, well, that tells us we have a minimum point. So let's take our first example that we've originally used. So y equals x squared minus 1. Okay, well, First we differentiate here to get dy by dx. So dy by dx. So dy by dx here, well that would simply give us 2x. Okay, so that gives us dy by dx. And now differentiate again for the second derivative. So the second derivative here, well that means we just differentiate 2x again here. Okay, so if we differentiate 2x, that would simply give us 2. And now we take a look at this final line here. So as we can see, this isn't less than 0. Okay, 2 is clearly not less than 0. So it's not a maximum. The second derivative is not equal to 0. So it's not a point of inflection, but it's clearly greater than 0. Okay, so what that tells us then, as this is greater than 0, that this is a minimum point. Okay, so this is a minimum point. Okay. But you could have also figured that out using the graph here as well. Okay, as this would just be a quadratic, which would look something like that, and you would have your minimum something like that. Okay. Now, what about the second example that we used before? So let's just clear all this just so we have enough room here. So for our second example, we used y equals sine x plus cos x. Okay. Well, again, first thing we do here is we differentiate to get dy by dx, which is equal to f prime of x. So dy by dx here, what would that give us? Well, in that case, dy by dx is simply cos x. We differentiate sine x, you get cos x, and the derivative of cos x with respect to x is simply minus sine x. Okay. But remember, we now need to differentiate again to get the second derivative. So if we differentiate again here, we obtain the second derivative. And again, we just go along term by term here. So if we differentiate cos x, that would give us minus sine x. So we get minus sine x. And if we differentiate minus sine x, that would give us minus cos x. Okay, so minus sine x minus cos x. So that gives us the second derivative. We now need to test both our values of x for the corresponding value of the second derivative here. So for x equals pi over 4, so for x equals pi over 4, in that case, substituting this into our second derivative here, what we obtain, if we try to say in full, we obtain this is equal to minus the square root of 2. And clearly, this is less than 0 in value. So what that tells us then is we have a maximum point. Okay, so therefore, maximum point. Okay, and now we also need to consider the other point, which is x equals 5 pi over 4. Okay, so for x equals 5 pi over 4, what would we obtain here for the second derivative? Well, for the second derivative here, again, just substituting x equals 5 pi over 4 into our second derivative, what we obtain then is this is equal to the square root of 2. Okay, and the square root of 2 is just simply larger than 0. And in that case, that tells us we have a minimum point. Okay, so therefore, that is a minimum point. Okay, so that gives us everything we need there for finding the nature of stationary points. And finally, let's move on then to take a look at sketching graphs from information about functions. So let's say we have a complex function with multiple terms. So for example, f of x is equal to 1 plus x, so 1 plus x minus 2 cos x. Okay, and x is between minus 2 pi and 2 pi, okay, where this is measured in radians. Well, if we find the first derivative here, f prime of x, what would we get? Well, the 1 would differentiate to 0, the x would differentiate to 1, and the minus 2 cos x here would differentiate to 2 sin x. So we get plus 2 sin x. Okay? And here now we need to find the second derivative, so that's f prime of x. So in that case, if we differentiate 1 here, that would give us 0, and if we differentiate 2 sin x, that will give us 2 cos x. Okay? So therefore, any stationary points will occur when f prime of x is equal to 0. So in that case, 1 plus 2 sin x is equal to 0. So solving here for sin x, well, 2 sin x is equal to minus 1. So therefore, sin x is equal to minus a half. Okay, so therefore our solutions here for x within the correct range, the domain here, well, x is equal to minus 5 pi over 6 minus pi over 6, 7 pi over 6, and finally 11 pi over 6. Okay. What we need to do now is consider these four solutions here. Well, for x equals minus 5 pi over 6. Okay, so for x equals minus 5 pi over 6 here, our first solution, well, we can see f of x, so we substitute this value in. For f of x, we get 0.114, and for f prime of x, the second derivative here, we get minus the square root of 3. So what that tells us here, as this is less than 0, this is a maximum. Okay, so therefore, that's a maximum. Now we move on to the next solution here of minus pi over 6. And let's change our pen colour just to make this clear. So, this is for x equals minus pi over 6. Well, in that case here, for x equals minus pi over 6, f of x is equal to minus 1.256, and f prime of x is going to be equal to the square root of 3. Okay, and because that's greater than 0, that tells us this is a minimum. Okay, so we've done the first two here. Now we consider x equals 7 pi over 6. So for x equals 7 pi over 6, well, again, finding f of x by simply substituting this in, we get here that f of x equal to 6.397. And for f prime of x, what we can see then is we get minus the square root of 3. Okay, and again, just like we saw here, this is less than 0, so that tells us we have a maximum point. Okay, and finally, if we move on to our final solution here of x equals 11 pi over 6, so x equals 11 pi over 6. Again, just finding f of x and f prime of x. Okay, so f of x is equal then to 5.028, so 5.028, and f prime of x is equal to the square root of 3. And again, this is greater than 0, so like we can see here, this must be a minimum as well. Now what we've got here is enough information to start to sketch these points to give us a rough form. Okay, so make sure you take a note here of everything that we've got so far, because what we'll need to do now is clear this so we can get our sketches. So if we clear this information, what we can do now, like we said, is sketch these parts onto a graph to give us a rough form. And if we do that, we get something that looks like this. Notice these are our turning points, okay? Our maximums and our minimums. And we can be helped further in sketching by considering the behaviour of the graph as x gets really big or really small. We know that the graph roughly follows y equals x plus 1. So as x gets really big, so does y. And as x gets really small, so does y. And with this, we can finish our graph, okay? And we can see we should get something that looks like this. Okay, so that gives us everything we need there for sketching graphs from information about functions, and that concludes this Maths Made Easy video on stationary points.